Okay, this is lesson 13 for MAT 171, and we're working with polynomial functions and their graphs. This is out of section 3.1. And let's take a look at some notes. Okay, graph of a polynomial function, basically always smooth. Doesn't have any corners in it, so to speak. It has no breaks or corners. The end behavior of this curve describes the function as x becomes larger as a positive or negative direction if any polynomial is determined by its leading term. So the leading term that we're talking about is right here. The one with the largest exponent in it. And whether it's positive or negative, so that anything that, let's take a look at some notes real quick. If we have y equals 2x squared, we know that opens up and to the right, up and to the left. If we have y equals to a negative x squared, we know that opens down to the right and down and to the left. And if we have y equals 2x cubed, we know that we have, it opens up and to the right and down and to the left. And y equals to a negative x cubed, that's basically reflects about the x-axis. So now it was opening up, now it's opening down and to the right and up and to the left. So that any polynomial that has a leading exponent that's even is going to have an end behavior like x squared. If it has an even leading exponent, such as x to the 4th, x to the 6th, x to the 8th, and so on, but it has a negative coefficient, it's going to behave like a negative x squared, down to the left and down to the right. It may have other movements in between there, but that's basically how it's going to end up. Any graph that has an odd leading exponent, like x to the 5th, x to the 7th, so on, that's going to behave like x cubed. It's going to end up and to the right, down and to the left. Again, it will have different curves in between there, but that's how it will basically end up, like x cubed. And then if it has a negative coefficient with an odd exponent, then it'll behave like a negative x cubed, up and to the left, and then it'll do some curves, and then eventually go down and to the right. Alright, so let's continue on with these notes. And that's all that's saying here. The zeros of a polynomial where c is a number so that when you plug that in you get 0 out. Well, basically a 0 is just an x-intercept. So we could say that this would be c, comma 0. The zeros are the solutions to the polynomials. They're also known as the roots or the x-intercepts. So that's all zeros mean. And steps for finding our roots, just like what we've been doing before. Set y equal to 0. We have to factor the polynomial, and then set our factors equal to 0, and then solve for each factor. That's nothing new from what we've been doing already. Well, we also have to find our y-intercept too, right? By setting x equal to 0 and solving for y. Nothing different there. Okay, here we have what's called the intermediate value value theorem. And this is where we have a polynomial, we'll call it P of x, is a function. And if we put in value A and value B, and what they end up with are opposite signs, if they get one value is positive, another value is a negative, then there exists at least one value in between there called C. And the reason why they have this, excuse me, is that, and let's see what this looks like. Okay, here we have a graph. And in this graph, here's, let's say, value A. So if we put in value A in P of A, and we get a negative number out. Okay? And then here we have here we have value B. And we put in P of B in, and we get a positive number out. Then there has to be at least one value in between A and B that intercepts that x-axis. And we'll call this C. So that we would say that P of C, there has to be some value C that's going to be an x-intercept. So, why would we say this? If we have a table of values, and we're going to be working with table of values, if we have one number, let's say -1, and we get a, let's say we get a 2, okay? And then we have another one, 0, we get, let's say, a -3 out. Well, that means that in our graph, if this is our graph here, here's -1, 2, and here's 0, -3, that there had to have been some point in between -1 and 0 that crossed that x-axis. Okay? It may not have shown it in the table of values, but you know it has to be that. Okay, and that's all that's saying. Okay, steps for graphing our polynomial functions. We find our x-intercepts and find our y-intercept. We determine our end behavior by looking at our leading exponent and whether our leading coefficient is positive or negative. Then we graph it using the table of values. So let's take a look at some problems. And this first one here is one like you'll see in your textbook on problems 11 through 22 on page 262. And we're going to look at problem number 14. And here we have P of x is equal to, and these problems are already factored out for you. Not all of them will be, but these are. So we've got parentheses 2x minus 1, and then parentheses x plus 1. And we also have parentheses x plus 3. Okay? And that's